for making all the different time zones, and also it's great to see so many familiar faces. I think with that, it's my pleasure to introduce you today to our speaker, and I think it's about time that we get started. Today, I have the pleasure of bringing to you Andre Varji-Twara from Andrew Hauk's group. And hello, Andre. How are you today?
Hi, Zlatko. Very good. How are you?
Great. So since we've asked everyone where they're tuning in from, how about yourself?
I'm tuning in from Chicago in Illinois.
Wonderful. Well, thank you for accepting our invitation, Andre. Before we pull up your slides and get started, let me give a short introduction. Andre joined the Andrew Hauk Group in 2015 after finishing his undergraduate studies at the University College London. Andre is now the Kadanoff-Rice Postdoctoral Fellow at the University of Chicago as of 2020, jointly in the groups of Dave Schuster and John Simon. So I think with that, Andre, the stage is yours.
Thank you, Zlatko, for the nice introduction and for the invitation to give a talk at your nice seminar series. So yeah, today I'm happy to share some recent work I did during my PhD in Andrew Hauk's group at Princeton. This work is focused on coupling a highly nonlinear artificial atom to a photonic crystal and observe signatures of ultrastrong coupling and multimode entanglement. The motivation behind this work follows this growing interest of studying complex properties of interacting photons in the circuit QED framework. And this extends to the broad motivation behind quantum simulation, where many groups around the world are developing synthetic quantum materials and are inspired by these fascinating phenomena in condensed matter, where the general goal is to understand properties of an ensemble of interacting quantum particles. Here I am highlighting a few quantum phenomena such as superfluidity, superconductivity, and magnetism that belong to this class of interesting many-body problems. And some of the open questions that people are interested in are in finding a phase diagram, understanding how the ground state changes with system parameters, as well as studying the system dynamics following a quench, for example. And these problems can be hard to solve. In fact, for systems beyond the, let's say, 50 particles, it becomes an impossible task with the classical computing hardware. And to overcome this obstacle, starting with Feynman's proposal in the 80s, people have suggested this concept of building artificial quantum matter that can emulate the many-body Hamiltonian of interest. And experimental progress in the past 30 years has made it possible to control and manipulate individual quantum systems in a variety of platforms. And to name only just some of these promising platforms, you have cold atoms and optical lattices or arrays of optical tweezers. You have trapped ions, and you also have interacting photons and superconducting circuits, which is directly related to the work we do in the Hauk lab. Okay, so to start off easy, I would like to give a brief overview of the main building blocks in a superconducting circuit platform. The simplest object you can make in a lab is a microwave cavity where a single resonant mode behaves as a harmonic oscillator. These oscillators can be made on chip using lumped element capacitors and inductors or coplanar waveguides, or they could be machined, or they could be 3D machined resonators. Of course, this toolbox would be limited if you only had linear elements, which is why we are fortunate to have Josephson tunnel junctions, dissipationless nonlinear component. And building circuits composed of Josephson junctions allows us to engineer artificial atoms with an anharmonic energy spectrum, where we have this capability to manipulate individual energy states of the circuit. The simplest qubit you can make in the lab is this weakly anharmonic oscillator, where you replace the inductor with a single Josephson junction. And you can think of this Josephson junction as a nonlinear inductor that lowers the resonance frequency of the oscillator every time you introduce an additional photon. You can also make even more anharmonic circuits by shunting a small Josephson junction with a large kinetic inductance, where now your energy states are encoded in persistent currents circulating in your superconducting loop. And the way you connect these two objects is using the circuit version of cavity QED. What you do is you couple the dipole of your Josephson circuit to the quantized field in the resonator. And this is a nice realization of the James-Cummings Hamiltonian, where the atom coherently exchanges excitations with the cavity. And in the world of circuit QED, this interaction strength can be very large. You can engineer qubits with incredibly large dipole moments, and you can engineer your microwave photons to have a very small mode volume and get enormous electric fields. And this gets you far into the strong coupling regime where G, your coupling strength, can be 3 to 4 orders of magnitude larger than your dissipation. And this is what makes superconducting circuits an attractive platform for engineering photon-photon interactions using the nonlinearity given by Josephson circuits. This is nicely shown in this experiment looking at a qubit resonantly coupled to a microwave cavity where the spectroscopically resolved multi-photon Rabi peaks set an effective energy penalty for exciting additional photons into your system. Quantum simulation in circuit QED uses the same toolbox, but we want to go away from this conventional picture of having one atom coupled to one photon. And in fact, we want to explore many body physics with interacting photons. And the community has developed a lot of the crucial pieces for building quantum materials with photons. The first piece is to confine your photons into a metamaterial and give it an effective mass. This is something that the Haug group has pioneered using lattices of coplanar waveguide resonators with interesting band structure. The next crucial piece is introduce nonlinearity such that photons interact with one another, and there are various approaches to do that. In the Haug group, we started by coupling transmon qubits to every lattice site to introduce local interactions from the local James-Cummings Hamiltonian. You can also disregard the resonators entirely and just implement lattices of coupled transmon qubits as pioneered in the Chicago groups and the Google groups where you study Bose-Hubbard models. And there's also this approach of creating non-local interactions for using Josephson coupling elements as well, where photons now are predicted to have some form of a density wave ordering. Another important ingredient is to engineer sort of a reservoir to compensate for photon loss, because photonic systems are inherently leaky. And recent efforts have have dissipatively stabilized the photonic insulator using such a reservoir under the action of a drive. And also, if you want to study topological materials, there are techniques for creating artificial magnetic fields for photons. And this can be done either by modulating the complex tunneling between lattice sites, or another way to break time reversal symmetry is to also couple your lattice of 3D resonators to couple those mode to magnon excitations to break time reversal symmetry. And after having discussed all these platforms, I would also like to quickly highlight some of the recent work I'm involved right now as a postdoc with David Schuster and John Simon's groups at U Chicago, alongside the grad students Brendan Saxberg and Gabriel Roberts. We are studying lattices of coupled transmons. This circuit maps to a Bose-Hubbard model where you can think of the capacitive coupling between transmons to lead to nearest neighbor hopping between lattice sites, and the on-site photon collisions arise from the energy penalty induced by the transmon anharmonicity. Our near-term goal is to prepare a correlated superfluid state. This involves initially preparing a localized, and I'm showing here a theory to this proposal. This involves initially preparing a localized Mott insulator state by exciting half of the lattice when the transmons are detuned from one another in this staggered fashion. And then we slowly bring them into resonance such that we follow this adiabatic phase transition into a delocalized superfluid state. And what we want to do ultimately is to measure long-range correlations and entanglement that emerge as we go through this phase transition. This work is ongoing, so stay tuned for exciting results to come. And to sort of end this motivation section with, I would like to end it with a general observation that a challenge with these platforms is that scaling these many-body circuits, it becomes experimentally difficult to fully control and characterize your system. In particular, if you take the example of a lattice of transmons, if they're flux tunable, you have to, and they have to be brought in resonance carefully. So you have to tune crosstalk matrices, and as well as when you actually, even before that, when you fabricate your device, you have to make sure that your junctions, their energies, are made in such a way that the range of flux tunability allows you to actually create a lattice. And it's a challenging task, but it's a worthy one. And I would like to highlight in this slide just the proposal for engineering quantum simulators differently in synthetic dimensions. This idea came from a previous experiment where we operated a harmonic oscillator as an effective qubit using a dynamically activated nonlinearity. We achieved this by engineering a free-wave mixing process with an ancilla cavity, and we strongly hybridized the two-photon state with the application of a periodic flux drive. And this allowed us to control arbitrary states in the single photon manifold. So we extend this theoretical proposal for harnessing this stimulated nonlinearity for efficiently engineering photon interactions in a synthetic lattice. And this involves, for instance, shown here, coupling our nonlinear free-wave mixing elements to the discrete quasi-momentum states of a waveguide, where if you apply, let's say, the appropriate frequency selective flux tones, you can hybridize the two-photon states of all the momentum modes that have different frequency, and you can control that interaction strength. Also, using the free-wave mixing nonlinearity, you can apply a charge coherent drive that would allow you to propagate. It will allow you to couple any two momentum sites by simply applying a drive at the frequency that corresponds to the frequency difference of your modes. And what you have is that in this rotating frame of all these drives, you have photons that can propagate between momentum sites and experience on-site interactions. And we benchmark this idea by, for instance, doing numerics on a strongly interacting one-dimensional lattice, and found that under a uniform drive, we can prepare a crystalline phase of photons as highlighted by the oscillating density correlators. And to sort of sum it up, this kind of shows an attractive platform for studying strongly correlated quantum systems, where we have full control over the lattice connectivity, its dimensions. We can basically program potentially an arbitrary lattice by applying the appropriate charge drives, as well as we can control the magnitude of photon interactions by controlling the amplitude of your flux drives. However, so this was a nice motivation to move on to the outline of the talk. I've shown systems where you have lots of qubits and they couple to each other, and you're trying to look at the complex phenomena that arise from their interactions. In this talk, I want to look at something that seemingly seems trivial, but in fact it is not. And particularly, I'm showing an experiment where we're exploring many-body effects, where we only have one artificial atom, and it's coupled to the many discrete modes of a photonic crystal lattice. And the reason why this is non-trivial is because we push the coupling strength to go into these ultra-strong coupling machines. And what I'm going to show you today is going to be categorized in two types of experiment. The first one is we're going to investigate the single photon response of the system, where the propagation of a single photon effectively becomes a many-body problem that is influenced by the bound states in the system and the counter-rotating terms in your Hamiltonian. And also you look at the multi-photon response of the system, where the action of a strong drive, where you're introducing more than one photon into your system at the same frequency, this leads to an inelastic emission of correlated photons. Okay, so so that was the outline. So this idea of coupling emitters to sort of a waveguide, which is sort of the idea of integrating atom-light interactions in photonic crystal. This has been a long sought goal for exploring many-body physics in quantum optics. And in particular, Jeff Kimball's group has been strongly pushing this effort using cold atoms. At Princeton, we've also been exploring similar band edge physics in the microwave regime, where we strongly coupled a transmon qubit to the band structure of a stepped impedance waveguide, which you can also use as a Purcell filter. And we've observed for the first time atom photon dress bound states that live inside the band gap and have an exponentially localized photonic component. And we also mediated the coupling between two transmons for their bound states towards this goal of mapping this platform to an effective spin models that have long-range interactions dictated by how spread out the bound states are to one another. But the focus of this work is, instead of coupling many qubits to a photonic crystal, we want to investigate the many-body effects that would occur if you had a single atom coupled to such a structured environment when we start to push the coupling strength beyond the single particle regime. And in fact, Circuit QED, again, is an ideal platform for pushing the limits of light-matter coupling. As was pointed out in these reviews, I've hinted at it previously when I mentioned that the coupling strength can be made 3 to 4 orders of magnitude larger than the inherent dissipation. But ultimately, Circuit QED is also a good platform for engineering coupling strength that is now comparable to the intrinsic energy scales of the system. And to highlight this, I'm going to point out that there are fundamentally two ways of coupling a Josephson qubit to a resonator. The common approach that we mostly use is to capacitively couple the qubit charge degree of freedom to the resonator voltage. And the coupling strength can be written in this normalized generic expression. And as you can see, in order to get the large couplings that are comparable to, let's say, the cavity frequency, we need to increase the coupling capacitance. We need to increase the resonator impedance, possibly using kinetic inductance. And we also need to engineer a qubit with a large dipole moments. And ultra-strong coupling limits with charge coupling has been achieved. It is just a bit harder to do, because what will fundamentally limit your coupling is the fine structure constant, which is a small number. And it's a similar limitation in cavity QED for a Weber atom dipole coupled to the electric field in a cavity. And again, the difference in fine structure constant exponents just comes from the fact that the field in your resonator is in quasi one dimension. Okay, so to overcome this limit and actually take advantage of it, the second approach is to inductively couple your qubit to the resonator current, as shown here. And this is analogous actually to the magnetic dipole interaction given by, and then you can reach this, it's analogous to the magnetic dipole interaction, where you can take your qubit to have an effective magnetic dipole, and you're coupling to the magnetic field of your resonator. The normalized inductive coupling takes on this generic form, where again, in order to get large couplings, you need to have a large inductive participation. But in this time, you have to decrease your resonator impedance, which is an easier engineering challenge. And you have to have a qubit that has a large magnetic dipole moment. But the takeaway message, as I mentioned previously, is that the inductive coupling gives you this dramatic advantage because the fine structure constant enters with a negative power. And in fact, if you put in regular numbers for resonators and also for qubits, you can reach coupling strengths that are of order or even more than your cavity and qubit frequencies. And there have been already recent experiments that have reached this novel regime of light-matter interaction. For instance, in a single mode case, coupling strength between a single microwave resonator and an artificial atom has reached values that are comparable and even larger than the transition frequencies of the uncoupled system, where you start to see strong spectroscopic deviations from the James-Cummings model. And these deviations come from the fact that you have counter-rotating terms in your Hamiltonian that you can no longer eliminate using the rotating wave approximation. And then this coupling regime has been extended beyond the single mode picture. There have been a number of experiments coupling artificial atoms to a discrete set of modes, with recent results demonstrating that the coupling exceeds the frequency spacing between modes, or so-called the free spectral range, showing that the qubit can simultaneously hybridize with many modes in the same time. And this regime has also been extended to the continuum by using a linear waveguide where the spontaneous emission rate of the qubit is comparable to its resonance frequency. Our work, as you will see, falls in this category of multimode cavity QED and follows a different story from previous studies as we are coupling the qubit to a structured environment where, as I mentioned before, we have these band gaps and therefore we have these bound states that enter dynamics. Okay, so we model and implement our photonic crystal as a one-dimensional chain of coupled cavity where the artificial impurity is coupled to a specific cavity site. We can rewrite this tight binding model into a spin boson model, where in this rewriting it in the eigenmode basis, where the qubit is now coupled to each lattice mode. And as I said, this bosonic BAF has a nonlinear cosine, a bounded nonlinear cosine dispersion, where its finite bandwidth gives rise to photonic bound states. And we are interested in exploring how the transport of a single photon in the waveguide changes when we have these localized states and when the coupling strength itself breaks the rotating wave approximation. This diagram here shows how we're implementing this model with superconducting circuits. We use a chain of coupled microwave resonators as a photonic crystal, and as a qubit, we're using a fluxonium circuit. That is a ring of a superconducting ring that's interrupted by Josephson junctions. And we galvanically couple this fluxonium to a resonator site by sharing a portion of its inductance. Okay, so here I'm showing the optical image of the device. The photonic crystal is this snake-like structure. It consists of 26 coupled lumped element microwave resonators. And we implement the inductive coupling between the fluxonium and this resonator as a chain of DC squids. And this allows us to tune the coupling strength, because as we apply magnetic field to, as we apply magnetic field, it allows us to tune the inductive participation of the fluxonium. The reason why we also choose a fluxonium is not just because we can inductively couple to it, but also it is because at some ranges of the flux bias, we can achieve large magnetic dipole moments. And we only have one flux bias line in the device, and by applying a current or by applying a magnetic field to these two loops, it allows us to periodically tune the energy structure of the fluxonium as well as the inductive coupling. And we can do that independently because the current needed to introduce a flux quantum into the large fluxonium loop is much smaller 15 times smaller than the current needed to introduce a flux quantum into the squid loops. And this large asymmetry allows you to independently change the fluxonium energy, its transition frequencies, independently from the coupling strength to the metamaterial. The first thing we do in the system is we probe transmission for the photonic crystal waveguide using a very weak drive in order to look at a single photon response. And we sweep the drive frequency around the lattice modes, the band of the lattice. The frequency resolved resonances in these 2D plots correspond to the lattice modes of the photonic crystal that are hybridized with the fluxonium. And as we tune the magnetic flux, we bring the fluxonium in resonance with the band and observe a clear extinction in the transmitted power over several modes. And if we look at the transmission trace at, let's say, half a flux quantum, where the dipole moment is the largest, we fit this transmission trace to the model of a two-level system coupled to a waveguide, and we estimate the spontaneous emission rate that is comparable to the qubit frequency. We also fit our parameters, which I'm not going to go into detail here, to estimate how large is the coupling strength in the tight binding model, and we find that it is comparable to the resonator frequency. And from these two observations, we expect this device to be in a regime where the qubit is simultaneously hybridized with multiple modes of the environment, and the total number of excitations is no longer a conserved quantity. Since we have this capability of tuning the coupling, I will show you snapshots of the transmission data in increasing flux bias values, where the qubit enters the band while the relative coupling strength is increased over a much larger period. And okay, so we start with a transmission spectrum that looks similar to the previous slide that I showed. And as we increase the coupling
and maybe, Andre, here's a good, I think we're getting into the thick of it, and there's a few questions from the audience. Maybe I'll just slow you down for a second. Could you remind us, a question from the audience, could you remind us what the T term in the on the previous slide was?
Yes. This, right? So T, basically what I'm plotting, the S21, that is the magnitude of T squared. So
okay,
this is the transmissivity, the frequency-dependent transmissivity.
Okay.
It depends on the so gamma 1 is the effective emission rate of the qubit into the waveguide, as you treat the waveguide as your artificial bath, right? So that would be the effective T1 of the qubit going into the waveguide. We want a very strongly coupled our qubit to the waveguide, so that's why we observe a large emission rate that's coupled, that is comparable to the frequency of the qubit, and this is already a multimode signature. Gamma 2 is the decoherence rate, and the delta omega is basically the detuning of your probe from the resonance frequency of your qubit.
Right. And what would be the frequencies of each of the sites in the lattice on their own, if they were not coupled?
Around 7, because if you forget about the qubit and just have a chain of coupled sites of energy omega, then the band structure, as I showed here, well, this is delta omega k, but it will be centered around the uncoupled frequency, which in this case it's around 6.9 gigahertz, and the bandwidth is roughly 4 times the tunneling rate. And in this case, the tunneling rate is around 800 megahertz.
Gotcha. And in this transmission amplitude, are we seeing all the modes of the chain, or are they cut off by the instrumentation?
So there is one particular mode that gets pushed out of the band because of the fact that this coupling inductor renormalizes the frequency because it introduced an additional inductive term in that resonator. So it pushes its frequency a little bit outside of the band. But apart from that mode, you are seeing all the other n-1 modes within the band of your photonic crystal.
Mm-hmm.
And the reason why you see this sharp drop is the fact that your density of states, right, sharply, drop down as you go into these band gaps. And how sharp you drop depends on how many unit cells you have.
Yeah. And maybe you said this already, but could you remind us why the dip is at the site that it's at?
This dip would be sort of at the dressed qubit frequency, in the sense that these peaks that we see are the dressed modes of the lattice with the qubit, and also the dip corresponds to the dressed ground to first excited state of the fluxonium. And the reason why it is a dip, the reason why you see an extinction in the transmitted power, is because maybe I can go here. So you have a destructive interference between the incoming probe and between the incoming probe and the wave that's being emitted by the fluxonium, by your qubit, because as you apply a tone and that tone is closely resonant to your dipole, to your qubit, now the dipole also will start to emit in both directions its own fields, right? Mm-hmm. But if you drive it resonantly, that field will destructively interfere with the field that you propagate through the photonic crystal, this blue photon, because they're pi phase shifted, and that's why your transmissivity will go down. In fact, that is a measure of how strongly you are coupled. How much of a transmissivity extinction do you get when you are resonant with a qubit?
Is maybe an equivalent way of saying that, or maybe it's a bit different to say that on resonance here, your first qubit site looks like a short electrically. So the wave that you send in just bounces back and doesn't transmit through.
In some sense, but the measurement we're doing is we're not measuring reflection. But yeah, no, in some sense you're right. Most of the photons will be reflected. And either the photons that you measure out through this port, that's where we measure, like that's the output port that we use for all of these experiments. Yeah, you can think of it as a short. Either nothing propagates, or whatever propagates through the qubit can interfere with the wave as it's pi shifted.
Mm-hmm. Good. And maybe we'll talk about this later, but could you just tell us a little bit more about the geometry of the device here? Why it has this structure that we see? Sort of, you have these very large, I guess the coupling capacitors maybe make some sense, but then, the sort of large cutout region in each of the devices in the middle. Maybe you could just comment a little bit more on the design choices that led you to this particular shape of the sites.
Right. So each one of these boxes, I unfortunately don't have a zoom out image, but each one of these things are a unit cell, is a lumped element LC oscillator. This cutout box is where you have your inductor, and your capacitors are defined by interdigitated structure that are capacitors to the ground plane. This is the ground plane. Mm-hmm. And these elements here, these are coupling capacitors between each resonator. And these coupling capacitors ultimately give you the hopping term in your Hamiltonian. Mm-hmm. They're quite large because we wanted to have a very wide bandwidth band. We wanted 4T to be around 3 gigahertz, which is why you needed your coupling capacitor, which scales with the tunneling to be large. And the reason, well, a particular design reason why I chose to work with lumped element resonators as opposed to coplanar waveguide resonators that the people in our field use more, is because I wanted to compactify this this photonic crystal. Because if I were to implement the same photonic crystal with the same number of sites, 26 sites, but with coplanar waveguide resonators that had the same characteristic frequency, then I would have not been able to fit this on a 7 by 7 millimeter chip, but I would have needed to put it on probably a 10 by 10 or a 20 by 20 millimeter chip. So it was just for compactifying reasons, and also to possibly also remove some disorder.
And how much of a penalty in T1 of these sites do you take in, or is that a concern in this, since these lumped oscillators typically have larger participations in lossy elements?
I would say we don't particularly pay much. This platform, we want it to, what sets the sort of the dissipation of the oscillators themselves is basically the coupling to these 50 ohm transmission line waveguides, right?
Okay, because you're saying you're overcoupled in all these cases.
Yeah, I'm overcoupled. I can still differentiate all of these modes. I can still say with some clarity what the lattice modes are. I don't need to have them to be very coherent, because ultimately what I am interested in is how the qubit interacts with the modes. If that answers your question. And being overcoupled also allows you to extract your photons much faster, as I'll show later when I look at correlation measurements for all of these modes. If their coupling Q would have been much smaller, then I would have had to average a lot longer in order to get a good enough signal.
Thank you, Andre, for answering all these questions.
No, these are very good questions. So, as I was mentioning before, we have this capability of independently tuning the qubit, the fluxonium ground to first excited state transition, into the band, but also to tune the coupling strength of the qubit to the metamaterial, just by simply varying the applied current through our bias line. And this just comes from the fact that for a specific current, the flux that you introduce in the fluxonium loop that is used for tuning its frequencies, its energy, is 15. It has an asymmetry, has a very large asymmetry from the flux you introduce in the loop into the squids that is used to tune the effective inductor that you share with the cavity array. And what I'm going to show you is basically snapshots of where I'm changing the bias current, and I'm looking as the qubit enters the band, and I go to different regions where the qubit energies are the same, but the coupling is gradually increased. So let me go through those snapshots. This is a transmission spectrum that is similar to the previous slide, and as we increase the coupling, going to larger coupling points, we observe I would say a considerable lamp shift and an increase in the spontaneous emission line width of the qubit. But interestingly, as we increase the coupling further, we now see new spectroscopic resonances developing in the transmission spectrum, as I'm showing you here. And these extra features are suggesting that there are new states entering the scattering dynamics. And let me give a clearer picture of that. Here, I'm showing the calculated eigenstates of the joint qubit lattice system. And I'm calculating the eigenstates in the single, in the 1, 2, and 3 particle manifolds.
And could you tell us, when you say calculated, is this numerical, analytic, semi-analytic?
This is this is numerics. It basically, as I showed in the previous slide, I showed the tight binding Hamiltonian where I had my cavities with some energy, and I had a tunneling term between the cavities, and I had a qubit, a 2-level system. In fact, we even take higher excited states of the fluxonium as well, coupled to that one cavity at the edge, and then we just diagonalize the system.
Okay, so you have something like 30 modes, and one of the modes has 15 or 20 Fock levels, and the other one has 2 or 3, because it's a pretty big matrix, in other words.
It is a pretty big matrix, but so one way to go around that, right? Because it's a, like you said, it's a very huge Hilbert space. You start a problem by saying, well, I only care about eigenstates that have a total number of excitations up to 4 or 5 photons, right? And this allows you to truncate your Hilbert space to define sort of a new basis in which your Hamiltonian is now projected onto a basis where the total number of excitations that you take into account is less than 2 to the 15, right? And that becomes a much more tractable numerical calculation. And that's what we do here. Here, in fact, I calculated, what I'm showing you the slides, I'm calculating with the rotating wave approximation. And I'll show later numerics of how we do it without the rotating wave approximation. But essentially, since you have the rotating wave approximation, you can just diagonalize diagonal parts of your Hamiltonian that would correspond to having a total number of 1 photon, 2 photons, and 3 photons. And we did this just the way as to visualize what is going on with the states of your system as you tune your magnetic flux. Because what happens as you tune your magnetic flux is you change the energy of your fluxonium. This is the dashed line corresponds to the uncoupled fluxonium dispersion. And you also change its dipole moments as well, and therefore its coupling. So we wanted to get a clearer picture of what is going on that would explain where these extra states are coming from. And if that answers your question clearly.
Mm-hmm. Yeah, thank you.
And to go forward with this, let's say if our coupling strength was in the generic strong coupling limit, where G was larger than your dissipation, but G is much smaller than the, let's say, resonant, than the energies of your cavities or your qubit, then when you put in a single photon into your system, the dynamics is in some sense trivial because it is just confined to the single particle manifold. However, if you go to the ultra-strong coupling regime, we have these counter-rotating terms in your Hamiltonian, which is basically saying that we have these processes that involve the spontaneous creation and annihilation of pairs of excitations, of pairs where you put you create a photon into a mode, and you also excite your fluxonium, and also you do the opposite. You de-excite your fluxonium while you also remove a photon from your environment.
And quick question from Madhavan Palan. What does the crossing mean in the intersections of the 2 and 3 manifolds physically mean? If you could give us a little bit more of a picture of that.
Yes, that was the next thing I was going to say, is that usually, no, it's good. It's a very good question, because if you just take into account the counter-rotating terms, right, that add or remove pairs of excitations, that you should only visit you should only visit manifolds that have the same parity, right? So you should visit 1 and 3 and 5, right? But the fluxonium is not really a two-level system. We think of it more as a lambda system, where because you have these non-trivial selection rules, it allows you to actually visit manifolds that have different parities. That's why it allows you to go from the 1 to the 2 excitation manifold and from the 2 to the 3. And I can give a hand-wavy explanation for this. At certain flux values, your fluxonium has a non-zero matrix element that allows you to excite it from the ground state to its second excited state. That could be a plasmon state, right? So you go from 0 to 2, and then from 2, you de-excite back to a single mode into your metamaterial, and then from 1 to 0, that would be the de-excitation of the fluxonium. So you can see that that kind of freeway process now is breaking the conservation of parity. It's not breaking conservation of energy, but it is breaking parity. And to put it all together, again, we have counter-rotating terms and these non-trivial selection rules that no longer, that allows you to visit different excitation manifolds with a single photon. Not only that the manifolds have the same parity, but they can have different parities as well. Does that answer your question?
Yeah, thank you. And Madhavan, feel free to follow up on that in the chat, and I'll try to bring it up.
Absolutely. And the point that I want to make from this slide is that, in fact, these resonances that we see in the weak transmission measurements that appear are, in fact, the 2-photon and 3-photon bound states that are entering the single photon band. And the fact, and these multi-photon localized states become accessible to a single photon, again, due to the counter-rotating terms in the Hamiltonian and due to the non-trivial selection. Perhaps it would be good also to explain what I mean by 2 and 3-photon bound states. As I explained previously, that a single photon bound state, which I referred to previously as a bound state, was just a photon that was localized around the qubit position in space. And it's the same idea behind the 2 and 3-photon bound states. You just have multiple photons that are localized at the qubit position. And with a single photon, as it enters the waveguide, it gets scattered by these multi-photon localized states because you are in the ultra-strong coupling region. Okay, and going back to the data, we can confirm this with our numerical and theory calculations. Here I'm showing you the data together with the combined energy spectrum to confirm to some degree that these extra resonances in transmission is coming from here is showing this the 2-photon bound state, as is shown in this coupling limit as well. And we also see that for the larger coupling, we also see the 3-photon bound state entering the band, which reasonably matches what we see in experiment as well. And I would like to say that I would like to also add that we performed numerical transport simulations using matrix product states in order to simulate the scattering dynamics of the full system, where we take into account multiple levels of the fluxonium and we take into account the modes or the tight binding picture of your lattice. And we found particularly that these extra features, if I can go back as well, that the extra features that come into play in the data appear in our numerics for the scattering only when we introduce counter-rotating terms in our model. Because if we do not and we abide by the rotating wave approximation, we were not able to see in our numerics the features in the data, but we could reproduce them if we were not if we were to include these counter-rotating terms from the ultra-strong coupling. So that in some sense, conclusively kind of highlights that the propagation of a single photon through the system actually is sort of a many-body problem from the presence of these counter-rotating terms in the Hamiltonian. And and up to this point, we have probed, I would say, the elastic response of the system. And by that, I mean, we introduced a photon at some frequency close to the, inside the band of your metamaterial. And as we pump at that frequency, we monitor the emission at the same frequency. That's why I'm referring to it as an elastic measurement. And in this last part, I will present the inelastic response of this multimode system. As we pump the system at a particular mode, and we monitor the emission at different frequencies. We usually do this with a homodyne setup, and the way we sweep to look at inelastic emission of other frequencies is basically sweeping the frequency of our local oscillator.
I just wanted to appreciate the little animation. It's actually quite helpful. The quick question, so if I had to visualize the spatial distribution of, say, the fundamental here, the lowest frequency one, is And the highest frequency one is the highest frequency one where each site is exactly out of resonance there, and the lowest one is where they're all, well, I guess it's half a sine wave in the
Yeah,
distribution.
yeah. Yes, it's like these modes are the quasi-momentum, single particle quasi-momentum modes of the lattice. So um, the lowest mode would be, I mean, they're basically cosine of kx, where you can think of your frequency as you're sampling different momentum states, right? So the lowest mode would be a half a cosine, right? Like you said, and then as you go to larger frequency modes, you start to get more nodes, right? To get more oscillations.
Yeah.
Where the last mode is exactly as you mentioned, is basically uh, uh, pi shifted amplitudes at each site.
Okay. Yeah, and the leaky boundary conditions here don't perturb that picture too much. And
No, they do not. No, the leaky boundary conditions sort of, if I would say, if you can essentially, you could potentially tailor, and actually this is a good point, you could particularly tailor the boundary condition at your 50 ohm waveguide such that the band structure, your like passband of your filter, let's say, is very smooth, right? Because that's what you want for your filters, right? To have a very smooth, to have a sharp roll off, and to have a smooth, passband. You still end up with the same number of modes, but you can engineer your coupling to the waveguide such that you get a smooth sort of passband. However, in our case, um, since we're looking at this platform where we're interested in the dynamics between our qubit and our mode, and also effectively how the modes interact with each other, we would like to spectroscopically resolve each mode, right? And that's why we chose the particular boundary conditions with the outside waveguides.
I see. And the width of the modes, is it mostly set by, I guess when the qubit is off resonant from this band, higher frequencies, which appears at some of your frequencies, then the bandwidth of the modes is mostly set by the end coupler on the opposite side of the qubit. And I guess if the qubit is within the band, then maybe it doesn't matter so much. Maybe both of the couplers set the bandwidth of the modes. Is that roughly right?
To some extent, yeah, it is right. I would like to add that, let's say if I didn't have a qubit, which I've done this experiment, and I want to look at the spectrum of the photonic crystal without the qubit, obviously you're not going to get your extinction, your dip here, right? But the modes themselves will still have the same line widths. And those line widths are essentially directly determined by the spatial overlap of the modes themselves at the ends of the waveguide. Because you have 50 ohm, you have 50 ohm. Here, I'll just quickly go to here real quick because it'll be more. So as you mentioned, all of these modes, if you see, you can see them in frequency, and as you look at the lower frequency modes, there would kind of be like a smooth cosine going around the length of the chain, right? And the effective line width or kappa of each of the eigenmode is determined by how much of the mode lives at the edge, at the two edges, where you couple your input and output waveguides, because basically that is how you're inserting dissipation into the system for these coupling capacitors to the 50 ohm waveguide. So for instance, you saw that the lowest frequency mode has a very small line width because the participation of the mode itself at the edge, it's much smaller than the modes in the middle of the band, where they have a larger electric field participation at the edge.
Thank you, Andre.
Yeah, and of course, this also extends to the coupling of the qubit to all those modes, because the coupling of the qubit to the mode would depend on how much of that mode, right, participates in space to the resonator where the qubit is actually coupled to. right? But we'd like to look at the system more in a tight binding model, where we just think of the qubit as kind of being coupled to only to one cavity in real space, and do our simulations based on this tight binding Hamiltonian. Okay, so I showed this cartoon of how we think about and also how we actually implement this measurement of the inelastic response. I will particularly highlight the response when we pump the lowest mode of the photonic crystal. And again, emphasize that this is no longer a single photon measurement. We had to introduce many photons into the system in order to see the response that I'm going to show. However, given that this system, it is hard to actually quantify the photon number precisely. So all I can tell you is that we are definitely not driving. We are definitely driving more than one photon into the system. So what we see in this inelastic measurement as we are pumping the lowest eigenmode frequency, here I'm showing you the inelastic power spectrum, where we take our homodyne signal at each frequency as we sweep the local oscillator, and we look at the integrated power. And we look at this integrated power as we also increase the pump amplitude or the power. We keep the pump frequency the same, but we increase the pump power. And we see that as shown in this color bar, the area under the spectrum corresponds to the pump power. We see that for low drive amplitudes, we have a broad emission profile where we see most of the peaks aligning with the eigenmode frequencies. And then as we increase the pump amplitude above some threshold, above some critical value, the overall emission amplitude drops, and the spectrum has sharper resonances that are much closer to the eigenmode frequencies. And the way we can quantify or somehow understand this critical power threshold is from a separate pump probe measurement that as I'm showing here. This pump probe measurement involves doing the same transmission measurement as I showed in the previous slides. You have a weak probe tone around the cavity, around the band, and you have an additional tone, your pump, which you sweep its power on this y-axis. And we see that as we reach this critical power, we see that our dressed fluxonium resonance gets shifted in frequency, which is, given the nonlinearity of the system, this is where we estimate around this power, we estimate that we're definitely sending in more than a photon into the system. And particularly at this critical power, we see that the fluxonium resonance gets shifted outside the band and is no longer strongly coupled to the modes. And we believe that this transition in these two inelastic emission regimes can be explained in some sense simply by the qubit nonlinearity being diminished, being saturated by this strong pump. And the general observation is that the strong qubit nonlinearity induces multimode frequency collisions where pumping photons at one frequency, pumping multiple photons at one frequency generates photons at other modes. And of course, well, I would say for us, the interesting question that we wanted to ask is, these photons that are being emitted at these different mode frequencies, are they somehow correlated? And we tried various approaches. I'm going to go through them step by step. First, we investigated this following criteria for two-mode entanglement that has been developed and used frequently. So this has been developed by Hillary and Zubairi. This is a useful inequality that holds for any form of separable state, which means that if you have a two-mode state that violates this inequality, and implies that your two modes are entangled. And what this measurement involves is measuring the expectation value for the simultaneous emission of bosonic modes, and basically follows a straightforward application of the Cauchy-Schwarz inequality. The way we perform this measurement is basically we take the signal that's coming out of our waveguide. At room temperature, after our low noise amplifier, we split it into two separate homotime detection schemes, where we set the LO frequencies to the modes that we want to correlate the emissions of. And the expectation values for the photon intensity and for the two photon correlations can be extracted simply from second order moments of the signal with the appropriate cancellation of the noise from your Hemped amplifiers and also calibration of your Hemped gain. And again, as we characterize the entanglement between two specific pairs of modes by simply calculating this correlator. And if we find that this correlator is larger than 1, as it violates this inequality, this implies that the two modes are entangled. It is worth mentioning that this is a sufficient but not necessary condition in the sense that you could have two modes that still satisfy this inequality, but they can still be entangled. And though what we do next is, since we're getting an elastic emission over all the modes in the band, we measure this entanglement metric for all pairs of waveguide modes. And here I'm showing you snapshots of this map of the two mode correlators. And I'm showing you how this map evolves also as we increase the pump amplitude. And as a global metric, since we see that for every map, there's some form of global agreement between whether or not this correlator is above 1 or below 1. So as a global metric, we take the sum of all the correlators within a single map for a particular drive amplitude. And we plot this here as a function of our drive amplitude. And we find that as we drive the waveguide up to that critical amplitude, this leads to an inelastic emission of squeezed pairs of photons. I would like to clarify that the pump amplitude here is in normalized units of voltage given by our AWG. It's not in the same power units as used in the previous slide. And so this was one approach. It seemed to kind of emphasize that there is some form of entanglement into the system, but so far the metric in which we looked at this was just looking at the emission of two particular modes and asked the question, are these two photons coming out at these two different frequencies, are they entangled? It doesn't particularly measure how much they are entangled by, but it essentially just, it's more of a binary, it's just a binary answer to whether or not it's entangled. And then we moved on, and since this is a multi-mode system, in order to quantify the entanglement for more than two modes, we essentially treat this as a generic n-mode continuous variable system, and where we have sort of these phase space observables corresponding to the quadrature amplitudes that we measure in our inelastic measurement. And we define, basically, we have defined this covariance matrix for all the quadrature pairs. And the reason why we do this is because we're going to use an entanglement test that relies on partitioning this multi-mode system into two subsystems. We evaluate the partial transpose of the covariance matrix, and we use this what is called the positive partial transpose criteria that tells us that all separable states should satisfy this condition, meaning that the partially transposed covariance matrix together with the commutation matrix should be a positive semi-definite matrix in the sense that all the eigenvalues should be positive. And if this is not the case, then this implies then that your n-mode system has bipartite entanglement. And the way we choose our bipartition, for instance, although we have not seen any difference, is that we can choose, for instance, some modes to be in subsystem A, therefore their quadrature variables will have this index A, and some other modes will be in subsystem B, and their quadratures will be in subsystem B. And basically, this bipartition will effectively determine how you do your partial transpose. Here I'm showing you how the measured covariance matrix that we measure changes as a function of the pump amplitude again, as we did for the map of the two-mode correlators. And here I'm showing you the calculated, here I'm showing you the maximum eigenvalue of this matrix that changes because our covariance matrix changes. And we find that as we increase our pump amplitude, we are getting negative, eigenvalues much larger than the error bars, which implies that we indeed have bipartite entanglement up to the critical drive power. And then as we increase our drive power, we see that the lowest eigenmode approaches again to 0 to within its error bars, where it's hard to say whether or not we have bipartite entanglement. And since we calculated this covariance matrix, we will use a different method to say something beyond just looking at bipartition, but look at an approach for detecting entanglement in a multipartite system. And this has been proposed using quantum Fisher information that has been widely used in quantum metrology measurements for bounding the precision on parameter estimation. And this method has seen great success with discrete variable systems such as spins and cold atoms, and has also been applied recently to multimode continuous variable systems, which is relevant for this experiment. So this criteria is written here. We have the for separable states. We have that the Fisher information, which is on the left-hand side, this determines the sensitivity of this multimode Gaussian state to local perturbations, which in this case, these perturbations are local displacements of all these modes. They can be arbitrary local displacements. And we have that for separable states, this Fisher information is bounded by the it is bounded by the local variance of the uncorrelated state, which we simply evaluate by calculating the variance for the covariance matrix by removing all by removing all off-diagonal correlations. So we applied this criteria for our multimode system, where the Fisher information directly maps to the inverse of the covariance matrix, and the local variances relates to the covariance matrix of the uncorrelated state. And we have this inequality that is saying that this matrix for separable states should only have negative eigenvalues. And we evaluate it says here, so we evaluate the eigenstates of this system, and we find indeed that actually we get positive eigenvalues as we change the pump amplitude, which is again indicating that we have entanglement in our system. But given that this criteria looks at each mode being a separate partition, it actually says a bit more. It says that we have multipartite entanglement. And to sort of conclude this sort of study, as we are seeing signatures of multimode entanglement, I believe that in future explorations, we could consider adding qubits to our waveguide that could act as photon counters in such a way that we could actually measure what are the photons, how many photons are being sent to the system, how many photons are being emitted at each mode, and allow us to look at sort of to look at these correlations more precisely in terms of the photon number operators. Of course, as it goes with these many body systems, it's very hard to do tomography or to characterize the system by measuring the full density matrix given the large Hilbert space, which is why methods based on the covariance matrix and also that two-mode squeezing operator, they are quite useful in the sense that the measurement itself is less complicated than having to measure the full density matrix of your multimode system, which is quite large in this case. Okay, so with that, I would like to conclude this talk. We have realized the ultra-strong coupling regime and multimode photonic crystal. We have found that multi-photon bound states and counter-rotating terms dramatically modify the elastic transmission of a single photon, and that the strong nonlinearity of the qubit allows the driven preparation of strongly correlated multi-states of light. As an outlook looking forward, we were trying to probe the entangled ground state of the system, where this is quite interesting because entanglement can emerge just by simply coupling the qubit to the multimode environment without having to introduce any photons into your system. The ground state itself should be entangled. It's quite a it's a difficult measurement to do, since since it involves measuring emission from a ground state. However, there have been a few proposals using parametric interactions where you can prepare your ground state multiple times and see using virtual photons and see what actual photons come out of your waveguide. Additionally, we have this theory paper where we've studied the frustration of decoherence when the qubit is coupled, in this case, to two separate baths with non-commuting operators. And this is something we're also looking forward to implementing with an experiment. And with that, I would like to acknowledge the Hauk Lab and my PI, Andrew Hauk, for his membership, for his mentorship and leadership throughout the project and throughout my PhD. And last but not least, I would like to acknowledge our collaborators, the theorists at the University of Maryland, JQI, Alexei Gorshkov and his group, Ron, Rex, and Seth. I would say similar to this experiment where you can think of this fluxonium being like myself. It is a very boring object if you just leave it as it is. But if you couple it to multiple modes and you couple it very strongly, then you get some interesting effects. So in some sense, this is me being surrounded by a sea of theorists, and this has been a very productive, a very lucrative collaboration. And I acknowledge, I'm very thankful for their support.
Thank you. I
With
think
that,
we'll take that piece of wisdom home.
Yeah, with that, I'd like to thank you again, Zlatko, for the invitation, and thank the audience for their questions and for tuning in. Thanks.
Thank you, folks. We do have a couple quick questions before we wrap up. Question from the audience: can you remind us what the qubit frequency was during those entangled tests? Do you study how the covariance matrix depends on the qubit frequency?
Yes, that's a good question that I skipped over. Oops, sorry. These measurements were done only at the flux values where only when the qubit transition frequency was at half a flux. For two reasons. That's where the coupling was the largest, because the dipole matrix element, right? The matrix element with the phase operator is the biggest. And also, these measurements took a long time to do. So we decided, especially not because we measure the covariance matrix at a few flux points, but also we do measure these covariance matrices and these entanglement matrix for a large number of points in the pump amplitude axis. And as you can note, as you notice, that these measurements take quite a long time to generate a single map. And then you have to generate this map for like around 30 amplitude points and so on. So that's why we decided just to focus on the coupling points where the coupling was the largest.
Great. And the qubit here is below the band at half a flux.
It is inside the band.
It is inside the band.
The cartoon here is basically, I'm looking at half a flux where the qubit has to be inside the band. If it is shifted outside the band, then we won't get coupling to the modes as strongly. So this is showing the snapshot of the transmission measurement, where the dip shows you that the qubit is, the dressed fluxonium qubit transition energy is inside the band.
Oh, okay, that's what I would have thought. Maybe maybe I forgot what the figure means on the previous slide.
This one?
You see the line that goes below the band? Is that like a
Oh, this is the because I tried to color them, red would correspond to 2 particle states. So this is the 2 photon bound state that is appearing here, right? This is the free photon bound state that's appearing here. And this is this sort of the dressed single particle resonance of the fluxonium, the 0 to 1 transition, the fluxonium that is inside the band.
Okay, thanks. Yeah. So I guess this 3 photon bound state has lower energy. Or lower transition frequency, sorry.
Yes, for this particular coupling point, we essentially measured these covariance matrices and these entanglement tests for these particular coupling points, where we looked at half a flux, where you start to see the 2 photon bound state enter here, you start to see the 2 photon bound state go down, and then as you increase your coupling, states from above are starting to now come down, and that's where you start to see the free photon bound state.
Awesome. And can you tell us about the pump? Like, I think there's some questions in the chat about does this heat up the fridge, 1, and 2, can you use this to maybe create an inverted temperature in the system?
We have not seen the temperature of the fridge increase with the pump amplitude. Perhaps I've been a bit, I probably overstated saying that this is a strong drive. I would say it's not that strong of a drive that would heat up your device. It is something that, of course, it's not a single photon drive, but it's something more that goes as like minus 30 dBm of power going into your fridge, which, to give some experimental context, that's not a lot of power to heat up the fridge unless you really, don't have that many attenuators. But it's still, the way this measurement was done, which I hope was done carefully by saying this, is that I try not to focus at very strong drive limits because the problem just gets more and more complicated. You want to look at very few photon problems. So I just looked at this inelastic measurement for each mode, and I increased the pump slightly above. So this is the normal power that I would apply to get single photon response. And I go just slightly, like 10 or 15 dBm. I basically sweep this power range until I start to see some homodyne signal coming at room temperature. Of course, if you increase the drive power, you start to see other weirder effects, which at that point I decided not to focus on. Because at that point, you could be seeing effects where the pump itself just starts mixing with the coupler or just kind of weirder other saturation effects. And with regards to the temperature inversion measurement, I think this is related to the paper on the single photon bound state that came from Andrew's group, where with a drive and parking, dressing your qubit with a drive such that the one dressed mode enters the band and the other one is in the gap. That's another way of thinking of like using this reservoir engineering schemes to create an effective negative temperature, right? Because your bath is in some sense colored, like at some frequencies it doesn't have any density of states, and in others you do.
All right. Well, thank you very much, Andre, for the great talk, and congratulations on the very nice results. Thank you, folks, for the many questions throughout the talk and for the lively chat today. Seeing as we're a good 20 minutes over, I think it's time that we thank you, Andre, and we thank folks for coming in. I think with that, this talk will stay recorded, so you can go back and rewatch it. Subscribe to the YouTube Qiskit channel to know when the next talks are coming up. And with that, folks, it's been our pleasure, and we will see you next Friday at noon Eastern Time.